Welcome everyone to our Cosmology seminar. I've just started the YouTube live stream, so hello everyone out there. Today we have Hugh Garsden, who has just joined us here at Queen Mary, and he's going to talk about towards detection of the 21 centimeter H1 signal at cosmic dawn using low frequency radio observations. Please take it away.
Okay, thanks. So I'm ex-Harvard CFA. I worked with Lincoln Greenhill, who was a PI on this project. We had lots of contributors, some of whom you will know, and they and I are still doing some of this work in the background. So I'll be talking about my work in 21 centimeter cosmology. I'll give a brief overview of 21 centimeter cosmology, then talk about LEDA, the telescope that we use, and give a brief summary of global 21 centimeter work. But I work mainly on power spectra. So I'll go into a bit of detail on that, which will contain some technical stuff about interferometry. I'll present the power spectrum that we have from observations that we made using a telescope in the USA. Following that, we did some simulations of noise observations to find what sensitivity level we could reach with the telescope. And I'll describe that and compare that with theoretical models. So this is a very hand-wavy overview. If we go back to the dark ages, when there are no stars, there's only the CMB and neutral hydrogen and dark matter, which I'll mention briefly. So the H1 may absorb the CMB at 21 centimeter wavelengths in its rest frame. It may emit at 21 centimeters as well. The reason for this absorption emission is the electron in the ground state has two spin states, and the energy difference between them corresponds to a 21 centimeter photon. So we can assign a spin temperature Ts to the H1. George Field did this back a while ago, and the spin temperature is basically just a measure of the ratio of the electrons in the spin states. So we can compare the spin temperature to the CMB temperature. If they're the same, they're in equilibrium and we don't see anything. If the spin temperature is less than the CMB temperature, we'll get absorption at 21 centimeter. If the spin temperature is greater than CMB, we'll see emission. So we derive a differential brightness temperature at 21 centimeter. This is an example. This is an equation that I took off NED, the NED site, showing the temperatures and cosmological parameters. The brightness temperature changes as the universe evolves and stars form at cosmic dawn. What do we expect to see? This is a simple model that was generated, well, I got it from a paper by Pritchard and Loeb. This shows the variability of the brightness temperature over time compared to the CMB. So the CMB is the dashed line, and the spin temperature wanders around. we've got temperature this side on the left, and then frequency and redshift. So this covers a wide time range. My work is at cosmic dawn, which is around here, which requires low frequency radio telescope observations. And we can observe at 16 to 46 redshift. The temperature changes are very small. So this is millikelvin. So that's what we're looking for, which is very small compared to the sky. There are several reasons for the change here in the spin temperature, and I put some turning points in red here that I'll just give a brief explanation of. So initially, everything is in equilibrium due to collisional coupling. We're looking at three temperatures here: the gas temperature, spin temperature, CMB temperature. So at point A, the gas and the CMB are expanding and cooling. The gas cools faster, so its temperature drops and takes the spin temperature down with it compared to the CMB. So that's this drop here to B. At B, due to expansion, the spin temperature decouples from the gas temperature, which is collisional coupling, and couples to the CMB via radiative coupling. So the spin temperature goes up to the CMB temperature. At point C, the stars and galaxies are forming, and we have lots of Lyman alpha emission. This drops the spin temperature down to the gas temperature, which has continued to decline relative to the CMB. So the gas temperature is going down, and the spin temperature drops down with it. The Lyman alpha emission achieves this with the Wolfhausen field effect. This effect results in an electron jumping up from the ground state, and when it comes back again to the ground state, it's in a different spin state. That's just the hand wavy explanation. At point D, X-ray heating begins. There may be supernova and X-ray binaries around. So it couples the spin temperature to the gas temperature, and both of them go up, and they actually go above the CMB. So you get emission, 21 centimeter emission signal. Then at E, the amount of H1 is decreasing due to reionization. So you get a death of the signal over time. Now that was one model. There are, in fact, lots of models. This is from Anastasia Fialkov, collaborator, who's studying power spectra and the sky average signal. So she's got the typical model in dark, lots of other models, which are probing the region of X-ray heating, and varying parameters such as the timing of the X-rays, how hard, soft they are, what is the extent of their influence, and what their source is. So this is taken out of Anastasia's paper. There has been a reported detection of a dip in the 21 centimeter signal by Bowman in 2018. It has some unexpected features. the trough is about 500 milli-K deep, whereas we're expecting about 100 milli-K, and it has a flat bottom, whereas we're expecting turning points. This has caused a flurry of activity and lots of papers attempting to explain this. There are possible causes being proposed, such as an excess radio background and dark matter and dark energy. And these are a couple of papers about that. You'll see that this paper calls it an anomaly. Anyway, no comment. So this signal that I showed is the sky averaged or global signal. We can get a power spectrum at some Z along here if we can observe with some spatial resolution over the sky and with a frequency range that gives us redshifted, gives us cosmological distances. So ultimately, that provides a region with 3D spatial extent that we can look at. So this is just looking at a box from the Earth. These are angles because we often, in interferometry, think of angles on the sky, and just some cosmological distance range along the line of sight. So we can observe the signal in the box and Fourier transform it to get a power spectrum. Just a note about this, we always are observing the sky within which the 21 centimeter signal is embedded. So we need to get rid of foregrounds and everything we don't want to look at, which I'll talk about a bit later. So there are lots of models for power spectra as well. This is from Anastasia again. So it's got frequency on the x-axis and the familiar, I hope familiar, delta squared power measure on the y-axis, which is now milli-K squared. And Anastasia mentions some of the effects that I've mentioned and plots them on the graph in these dots. The Lyman alpha, the X-ray heating, reionization. So again, the values, power values here, sorry, are very small, around hundreds of milli-K squared. I'll flip now to the LEDA project and its telescope and my work with it. LEDA is working towards a detection in both the sky average signal and power spectra. The PI, as I said, Lincoln Greenhill at CFA. We use a telescope and interferometer in California, in the USA. It has multiple dipole antennas on the ground. So here's a picture. These are actually LWA antennas sitting in Owens Valley in California. They allow us to probe Z range 16 to 46 over 30 to 85 megahertz, which gives us several epochs that we could investigate. We have many collaborators. At the moment, Lincoln is the only one in the group at CFA. So he needs to get more funding and some more staff. But we have lots of collaborators, so the work continues. My work is some on sky average signal, but mostly on power spectrum. But I'll just give a quick summary of where things are at with the 21 centimeter sky average signal and detection. We have the interferometer, but single antennas can be used for the sky average signal. There are particular configured antennas for this. We calibrate raw data to temperature and get a sky spectrum that you can see here with temperature and by frequency. We get lots of these sky spectra and integrate them to beat down the noise. Then we need to remove foregrounds and the CMB and look for a dip or a spike, something like what Bowman saw. Of course, this is a lot harder to do than to say. The hard parts are we need very high quality spectra from the telescope and good calibration. And we need to remove the foreground somehow using modeling or fitting. There are various techniques, and the Bowman paper goes into quite a lot of detail about how they did some of these things. But at the moment, we have a sensitivity down to about 700 milli-K, which is not enough to match with the Bowman trough, but work continues. I'll switch to 21 centimeter power spectra. This is going to get a little bit technical about interferometry. But for power spectrum, we use the interferometer so we get spatial resolution on the sky. The telescope has multiple antennas on the ground. So just looking from above, there's 256 in total. We correlate every antenna with every other antenna, which I've tried to depict here in the second figure. The antenna pairs are linked by what we call baselines of different lengths. And I'll be talking about baselines for the rest of the talk. They are up in lots of different directions. Each baseline measures a Fourier mode of the sky signal. And that's just a result of the correlation. The wave number of the mode is dependent mostly on the baseline length, but also on frequency. The amplitude of the mode is what we get from the telescope visibilities that I'll just call capital V. They're complex numbers that result from the correlation of a baseline. So I need to note that to get anything useful out of this, you have to calibrate the raw telescope data, for example, against the sky using sky source models. So this is a rough intro of interferometry and what we need to know. Oops, going again. To get a Fourier transform, to get a 21 centimeter power spectrum, we go back to this box and we're going to Fourier transform the signal in this box. So if we look at the box face on, that's the plane of the sky, and the interferometer gives us the Fourier modes from all the baselines it has. The Fourier transform of the sky is incomplete, so we just get a particular set of modes. The wave numbers of the Fourier modes are called K-perp, which means perpendicular to the line of sight. And ultimately, they are converted to inverse distance, which will be megaparsec to the -1. the K value increases with increasing baseline length, which is how we get different modes, different K-perp modes. Now, the 21 centimeter signal is isotropic. So we combine all the baselines with the same K-perp, which gives us a 1D Fourier transform perpendicular to the line of sight. What about the actual line of sight direction? We need to Fourier transform in that direction for each K-perp mode. This is just standard multi-dimensional Fourier transform. Do it in one direction, then another direction, etc. So we observe at lots of frequencies that correspond to distances or redshifts in this box, and line them up, get the amplitudes, which are the visibilities, line them up by frequency for a particular K mode, and Fourier transform them. So we get the transform along the line of sight direction. And that gives us modes we call K parallel, parallel to the line of sight, which are also converted to megaparsec to the -1. So with our different directions, we get a 2D power spectrum, K-perp, K parallel, and power in there, power values. However, there's a problem. In practice, we can't obtain this array of frequencies for a K-perp mode from an interferometer. Sorry about that, I'm pressing the wrong buttons. So we can't get this array, which is just all the visibilities arrayed by frequency for a K-perp mode. What do we get from a baseline? Well, if with a baseline, we measure multiple frequencies, but they're also at a slightly different K-perp. If we look at the array that we get from a baseline, it varies by K-perp as well as by frequency. And that's not what we want. We want these all the same K-perp. One solution you may think of is to just cherry pick around the baselines to find the array that we want. So get the visibilities at different frequencies for the same K-perp. However, that's basically impossible because interferometers are not built like that. If it was possible to build one like that, I'd like to build it, but as far as I know, it can't be done. So one may resort to binning strategies or use periodograms for Fourier transforms of unevenly spaced data. And that was actually periodograms were used by Barry in their work reported in this paper, but they're using a slightly different power spectrum method. However, there is a way out of this problem. What we're going to do is use this array because the K-perp modes don't vary a huge amount, we hope. There are limits to what you can get away with. But we will stick with this array and do the Fourier transform on it to get what we will call K-parallel modes, which are close enough to the true K-parallel modes, and assign an average K-perp value to these K modes. I could put it another way and say that the K modes and the K-perp modes are not orthogonal. That's what the problem is. This Fourier transform of this array actually has an exact interpretation. It's known what it is. It's a delay transform producing a delay spectrum. This was developed by Aaron Parsons. He put out a paper on how to use delay spectra for 21 centimeter power spectra, and a lot of telescopes that follow that, including HERA. I need to explain what a delay spectrum is, because it does something very nice for us. The modes of the Fourier transform, which produces a delay spectrum, the modes of the delay spectrum correspond to the time delay of foreground signals between antennas. So I've got a cartoon here on the right where I've got a point source, waves of emission, and these will produce a time delay between when the wave front hits each antenna. So I'll get to antenna 1 first and antenna 2, and the delay is along ground. So this has a very nice property, this delay transform, delay spectrum. It isolates all the foreground power into low modes of the spectrum. To understand what's going on here, we need to look at that array and realize that there's actually two types of signal in the array that we're looking at. We can interpret the array of frequencies as an array of distances, and that is what we want to do when we're thinking about 21 centimeter power spectra. So we're going to form a spatial power spectra along the line of sight just by having an array of distances. But within the array, if we look at it as an array of visibilities by frequency, this is just a spectrum. Excuse me. Need some water. And both of these signals exist in this array. So this is the array of visibilities by frequency for a particular K mode. When this is Fourier transformed, all of the foreground power goes into low modes. So this cartoon has the result of the Fourier transform, i.e. the delay spectrum, on the x-axis, power on the y-axis, and all the foreground power is going to be at low modes around the DC of the Fourier transform. So this is a Fourier transform with positive, negative sides. And the power of the foregrounds are contained within horizon. If you think about delays from sources on the sky, there is a maximum delay that any source can have, and that's when it's on the horizon. So delays from foregrounds can only occur within the horizon, so the power sits within the horizon. Outside of this, we can look for the 21 centimeter signal, because we interpret this region outside here as the actual spatial Fourier transform of the 21 centimeter signal along the line of sight. we can make lots of these delay spectra, one for every baseline. So if I take the delay spectra for a baseline, rotate it vertical, and then for all the baselines, stack them by increasing K-perp. Increasing K-perp means increasing baseline length, and increasing baseline length means a wider horizon. So as you go up in K-perp, the horizon expands, producing the wedge, what you may have heard of, the foreground wedge. So we look for the 21 centimetre signal outside the wedge. So this is a power spectrum generated from observations. It's generated at 48, from observations at 48 megahertz, or Z of 28. So we're in cosmic dawn. Use a 10 megahertz bandwidth, which gives us our line of sight box direction. And we use 4 hours of integrated data to beat down noise. So we can see that we do have a wedge. We have the horizon here, and we have the cosmic dawn window. Now, the 21 centimetre signal will be in this window somewhere, but buried by a huge amount of noise. If we look at the horizon, there's some spillover. There's 2 levels of spillover. I hope you can see here, just outside the horizon, there is some spillover here, and then a fainter spillover a bit further out. So I'm calling them level 1 and level 2. The level 1 spillover is not that uncommon in other experiments, and we have some reasons for that. I'll get to that on the next slide. The level 2 spillover, which is all this fainter stuff, we don't know what has caused that. So we have also some more leakage at low K-perp, and that is attributed to the fact that short baselines pick up a lot of diffuse emission, which pushes up the side lobes here outside the horizon. There's artifacts in the cosmic dawn window. This one is produced by a ripple in the bandpass. So a ripple across the frequency range that's caused by cable reflections in the telescope and hasn't been fully calibrated out. But what we can extract from this are power values, which are in these units, milli-K squared, and then per volume. But we convert them to the delta squared measure used in cosmology. And we take a one-dimensional K value, which is just a merging of the 2 dimensions. And we get at this K value for delta squared, we get up to 10 to the 12 milli-K squared, which is huge, far beyond the hundreds of milli-K squared that we require for a detection based on models. So why is that the case? Firstly, we haven't integrated enough data to beat down the noise. There's lots of telescope noise in here. Plus, there's a lot of systematics that I'll get to. But the spillover in level 1, just outside the horizon, is partly due to the fact that we have a low frequency resolution in our telescope, which produces not a lot of pixels in the Y version. I'm hearing a lot of stuff going on to chat or something, but I'm not seeing them. So the spillover at level 1 is due to low resolution in the pixels here, vertically, basically. Plus, we use a window on the Fourier transform that we do of that array for to get rid of edge effects. And we use a Blackman-Harris window, but basically most windows will cause an expansion, slight expansion of the wedge, and which for us at low resolution pushes it outside the horizon. So there are a lot of errors that are possible, and there are a lot of people investigating these errors at LEDA and in every power spectrum experiment, and they cause artifacts and other problems with power spectra. So I'll put these errors into a few different categories and mention them briefly. Firstly, we don't understand the telescope well enough. We don't understand the beam, which is used for calibration. There can be cross-coupling between cables in the telescope. There can be mutual coupling between antennas. We also don't understand the sky well enough. There's lots of diffuse emission at low frequencies, which we have not included in calibration. So that is going to produce calibration errors. And also, we may not have perfectly accurate source models. There also could be just bad data coming out of the telescope, such as undetected RFI or hardware errors where things have just gone wrong and there's glitches in the data. We also have to calibrate against the sky. And there are various calibration algorithms. Some are more sophisticated than others. We used a fairly simple one, which is self-cal. So all experiments are faced with these issues. So this level 2 spillover, I'm just going to dump into one of these and say something in there is the cause, but we don't know yet. So given that we have a power spectrum, it's obviously nowhere near good enough for a detection. We wanted to find out if we could get a detection, if we have enough data, and assuming that all these pesky issues are dealt with. So we're going to do that with simulations. Run simulations containing only telescope noise over a long time period, generate power spectra, find the noise level in the cosmic dawn window, which will be produced only by noise, and see if we can get a detection. Firstly, we need to get the telescope noise. We use a simple differencing technique. If you look at this array that we had for a baseline, just interpreting it as an array by frequency, adjacent visibilities are only separated by a small frequency step. The change in frequency is not that great between pairs of visibilities. So we difference them, which should give us just the noise. The true value of visibility should be about the same. So if we difference them, we get the noise. We do that across all the data and histogram the result. This is a histogram, which looks very Gaussian. The visibility difference values are in red and a Gaussian fit in blue, and they're very near to Gaussian. These the visibility values are in Janskys, which is what we get from the telescope. They are ultimately converted to power, but that's not important. The important thing is that we have a Gaussian distribution, which looks like thermal noise. However, it still will contain systematic errors from those issues that I mentioned previously that cause problems in the power spectrum. But we can use it as an upper limit for the noise. So we can get our a distribution of noise values, distribution for the noise values that we can use for our simulations. The other thing that I want to mention is that we need to change our integration scheme. I haven't talked about the integration scheme so far, but for the power spectra that we generated from data, we used incoherent integration. And we really need coherent integration, which gives far better noise reduction. So what does this mean? If you look at a bunch of observations over time, these are telescope observations, each one indexed by baseline and frequency. They come every 9 seconds. So there's a lot of them over 4 hours. For incoherent integration, we convert each observation to a power spectrum and then average them together. For coherent integration, we average them together first and then convert to a power spectrum. But for coherent integration, we need a very particular set of data, which is why we didn't use coherent integration for the power spectrum that I showed. Getting the right data for coherent integration is a lot harder because all the observations must be of the same sky, which can lead to years of observing every day, one observation at the same time each day, which is basically possible in practice. So we have settled for a mix of coherent and incoherent integration, where we coherently integrate a subset of data and then incoherently integrate. Once we've got our noise values and we've implemented our new integration scheme, we did a simulation of 3,000 hours of observing noise at 48 megahertz. In practice, because of the mixed integration scheme, this means 750 days at 4 hours per day, which is doable in real life. So we could actually make these observations. We get a power spectrum from these simulations, which is basically all noise. From that, we get a delta squared value at k equals 0.3, which is now 275 millik squared, which is great because now we're down to the sensitivity that we need of hundreds of millik squared. Our next step was to do this simulation at lots of different frequencies, not just 48 megahertz, but frequencies across the full band of the telescope. And we can then compare the sensitivities that we're getting to theoretical models. These models plotted here are from Anastasia Fialkov again. What we're looking at are power over time over redshift 1 plus z on the x-axis. Got delta squared on the y-axis. This is a subset of some of her models. And over the top of that, we have plotted in the crosses the sensitivity of the Owens Valley telescope using 3,000 hours of integration using that scheme, mixed integration scheme. I'll get to these models on the next slide, but the orange line is an exotic scenario motivated by the edge detection, i.e. an external radio background. Within the grey lines, there are models which have varying parameters. And for those who want to see them, these are the parameters that are varied that go into Anastasia's models. There are others, but these are the ones that are varied here. You can read through them if you want, but we have X-ray heating, so that's related to the X-rays. We have reionization parameters like optical depth and mean free path. That's an introduction to the plot. Whoops, doing it again. So these models inside the grey lines contain certain parameters that are varied. We have to show a subset because there's just too many of them. So if you're interested, the light blue, blue and dark blue lines vary the halo velocity, and the dashed blue vary the X-ray heating, I think. Yes, X-ray heating efficiency, FX. The magenta line is what Anastasia calls a standard physics model. And then the orange line is this exotic scenario with a radio background. What we conclude is that this sensitivity allows us to detect Lyman alpha and X-ray peaks, the highlighted region, this region here. So we have interesting stuff going on above the crosses in this region. These, the sensitivity allows us to constrain the timing of the coupling of the spin temperature to the H1 temperature, which is caused by Lyman alpha emission and the Withausen field effect, and also the timing of the emission of X-ray binaries, which produce heating fluctuations in the gas and the spin temperature. A full analysis of the roughly 10,000 models that she's got will give us the complete distribution of parameter values and models that lie above the sensitivity of the telescope. So that should just be the Owens Valley telescope. One way of doing that is using neural networks, and Anastasia's already been working with neural networks just recently, and will probably continue working on these models with neural networks. Another thing to note is that the orange line is above the crosses, and the orange line is the exotic scenario motivated by edges. So you may be able to study them with this level of sensitivity. So I'm basically done. I'll just make these points. We do have a delay spectrum type power spectrum at cosmic dawn, and there aren't many of those. Mike Eastwood, who was a grad student at Caltech, did generate a power spectrum from the Owens Valley telescope, but used a different method, M-mode analysis. There are other ways to get a power spectra that are used for other groups. You can make images and just take the foregrounds out of the images, or you can go more sophisticated and work with spherical harmonics, and there are other techniques. There will be other power spectra at cosmic dawn coming out as telescopes go down to lower frequencies, which a lot of existing telescopes are doing or intend to do. Our power spectrum has issues, and we need to work on the Owens Valley telescope data quality, but at the moment that's not going to happen because there's no support at the moment. Most of the work I did by myself, and a lot of it by hand. There's just not automated pipelines and all the stuff that astronomers need. We have a sensitivity that will get us a detection using 3000 hours, and we can constrain various parameters. So that gives us hope that in the future there will be a detection from this telescope. And that's the end. Thank you.
Okay, thank you very much for this talk. Before we start the discussion, let me just quickly conclude the live stream. So for the people watching on YouTube, you can leave your questions in the comment section. I hope you enjoyed the presentation, and I see you next time.